What is the John Laeter Center? Many of you may not be familiar. We're a core research facility at Curtin University. We have, at the moment, around $45 million in high-end microscope, mass spectrometers, diffractometers, experimental facilities, and a new additive manufacturing capability. Our research focus is largely on the strengths of WA industry, geoscience and materials, and environmental science. We have about 25 staff members who provide services both to our internal researchers as well as to external collaborators and on a consultancy basis as well. This is our mission. Our mission in the university is different from most of the schools. The schools are where the academics are housed and where students are trained and PhDs are granted. And our mission is different. Our mission is to build world-class analytical and characterization infrastructure. We're very much about research infrastructure. And the purpose of this infrastructure is to support research excellence, both in university, but also to foster end-user collaboration, both with industry and government agencies. We've got three themes. The technology theme about not only acquiring high-end pieces of equipment, and we're generally talking about things that are worth over $1 million, but also to integrate a workflow for this equipment so that we can take projects end-to-end from either when a rock sample is collected to an actual end date of a geological age and a publication or whatever somebody might be interested in. The key thing about infrastructure is that if you have good infrastructure, you can attract talent from around the globe as well as retain it. And we think we've done a very good job of bringing some of the best and brightest people to Australia and to Western Australia. And these people have in turn given back by developing new techniques and innovations, and so it's a positive cycle where we've been able to be at the cutting edge of many of the things that we do. But the other thing that we need to do is we need to make sure we have professional staff capable of maintaining this high-end equipment. That's where access and optimization comes in. We need to have highly qualified people who can deal with complex electronics boards, high vacuum systems, ion beam technology, laser technology. These people are really what keeps the center going. And so we have a program to bring these professional staff in and manage them, which is very difficult to do in a school scenario. But also these people help facilitate access to the outside world, to our equipment, and make sure they get the best bang for the buck when they come and collaborate with us. So that's the mission statement. Here's where we're at, mostly on Bentley campus. And the core analytical facilities are like our flagship facility is the Shrimp Uranium Lead Geochronology Center, which was started in 1992, I believe. And then these other areas in black I won't be talking about them today, but they are capabilities not only in the geosciences, but in other areas as well. I'm gonna brag a little bit about what we've got coming through in the future, which is the areas in the light blue teal color there, because I think it's really exciting for where we're going. But really what people come to work with experts at the Laeter Center, they come to address questions and answer questions. And most of it is, what is a sample? What is in a sample? What is the age of this mineralization? What is the age of this rock? And I'll go back to the very beginning. John Laeter, who was the professor of physics, who teamed up with the Geological Survey of Western Australia to bring in the first shrimp. And in 1993, there's the image of the team, and there's a newspaper on the console there which says "Atomic Machine: A Boon to Science." And it really has been. And John Laeter has had a fantastic career of leadership. There's streets named after him. There's buildings named after him. He was a very powerful intellect in the state. And we want to keep that legacy living and alive, and that's why we've named this. We've got 27 years of joint operation of the shrimp with the Geological Survey of Western Australia. And I think this is sort of the concept of partnerships that we really want to get across. We want to partner with you. We want to partner with our collaborators to get the best results. And that shrimp, when it was purchased in 1993, was a huge risk. I mean, it was an really relatively untested instrument. It cost at the time $2 million, which is about $10 million today, I believe. And it was a real risk for a small university at that stage like Curtin to stick its neck out and get this instrument in. That instrument, we just retired it and after 25 years of operation. After 27 years, we're still operating with the GSWA, and they have generated a very large volume of data, and we've had many PhD graduates supported and graduated using this tool. And this is an example of the samples that the GSWA has analyzed using the shrimp instrument. So I believe it's almost over 2,000 individual samples analyzed and it's literally transformed the geological map of Western Australia. From 1979, it was a pre-shrimp, to 2015. Yeah, the colors have slightly changed and the shapes, well, they're more or less similar. But when you look at at this legend, you can see the comparison in legends. And this is all about age data, age information, where samples exist relative to others. And this has really helped, I think, industry in particular to focus on areas of interest for exploration and development. So we do provide quite a few services. We're not only focused on earth sciences. We do a lot of microscopy work for the downstream sector, for like say investigating pipelines, for example, with the Corrosion Engineering Center. And we also do a lot of training of students. We do both collaborative and consultancy projects. So the consultancy projects, the intellectual property is 100% owned by the industry partner. But the majority of the industry work we do is actually collaborative, where they're happy after a period of time of confidentiality for that information to be jointly released. And Hugo Olyrook, who does a lot of our applied technology work, has a fantastic publication record because of this industry willingness to collaborate. A lot of into the geosciences, one of the tools that we use for everything as a tool that Neil McNaughton helped bring into the John de Laeter Center. It's an automated petrology tool. It's called the TEMA, made by T-Scan, and it's a robotic analytical platform for ultra-fast quantitative mineralogy. This is like the Ferrari of automated petrology. We still use light microscopes, but many students are hooked on this technology for getting them an answer very quickly. We can deal with both round mounts, polished thin sections, and polished blocks with this tool. And many companies, for example, from a Santos well, where they've used the tool to work out what the mineral changes were with depth. And in this case, you'll see there's a lot of plagioclase, orthoclase, and quartz, which you'd think, what is a oil and gas company drilling basically an igneous rock for? Well, in this case, the igneous rock is the reservoir for this promising gas field in the northern. So this is the sort of data you get. You get these mineralogy mosaics, you get quantitative analysis. You can actually deliver a table of grains. So here's what every apatite grain looks like in that slide, and the size of it from coarsest to smallest. And then you can actually use that map of that mineralogy to determine where you want to go next in terms of, should I take it to the shrimp or should I take it to the laser? And there's 3 different choices depending on what isotopes you want, what geochronology you want. And so it's a really powerful tool, and it's part of our mineralogy-based analytical, which I think you'll hear quite a bit about today. We also have something, and I just want to flag that, we take for granted good sample preparation facilities, but these are in jeopardy across the country. We've had a number of them closed down in the eastern states. Macquarie University, for example, ANU, a lot of the key geoscience institutions in this country are getting rid of their sample preparation facilities. We are able to keep it going here at Curtin because of the way we've integrated these into our workflow, but generally they start with using this new, new technology for us is a CellFrag, ultra-high voltage pulse fragmentation device to break rocks up, and then through a series of standard techniques, heavy liquids, Strands, to get into grains for mounting, and then we can polish those up and then put on a SEM or a laser system ion probe. And so we have both the ability to deal with rocks, as I mentioned before, or we can actually get mineral separates out. And so we have that capability here at Curtin. I'm just going to touch briefly on some of the newest facilities that we've got coming in or have just been established this year. And it's actually been a tremendous period of growth, unanticipated growth. And it's actually causing a bit of a problem for us. We have we're running short of places to put this equipment. So there's a new building in the horizon, so that will hopefully solve itself in time. But in terms of collecting a rock sample in the field, bring it into the lab. First of all, we do a digital mineralogy analysis. If you want to know trace elements, we can put it under the laser. We can put it under the focused ion beam system. We can put it under the TEM to get 2 nanometer resolution, or it can go into the atom probe, where you can get into these. This is an atom cloud here. Each of these dots is an individual atom that's been measured in a sample. And so here on this graph that's been put together and borrowed from industry, we have 10 parts per trillion, 1 ppm, 1 weight percent, and then we've got analytical spot size. So this is 1 centimeter. So you might take that sample, you might put it into an XRD, and you get semi-quantitative analysis, but you would definitely get to know. Whereas you go down here, where you're down less than 1 nanometer, you're in the APT, atom probe territory, where we have a facility that can do that. We've got a dynamic SIMS. The shrimp is a dynamic SIMS. Also, we've got a CAMECA 1300 coming, which also does that. Laser ablation sits very nicely sort of in the middle, and it's a go-to tool for determining which direction you go. Do you want to go to SIMS, or do you want to go to atom probe, perhaps? And so this is the sort of spatial dimensions that we're dealing with, and we're trying to populate for the broad community, which may want to look at things at the level, at the 1 nanometer level. And believe it or not, there are some companies out there who are looking at these things for mineral processing at the moment with us. So one of the new facilities is the time of flight secondary ion mass spectrometer. The instrument here, which was installed in February. Will Rickard is the facility leader for this tool. So this is called a static SIMS. It was funded by the Strand Research Council in collaboration with other partners. It's well over 2.5 million for this tool. And what it does that our current equipment can't do is it can work with organic molecules. And it analyzes the surface of samples, so it has like a penetration depth generally within 1 to 2 nanometers. But it can actually not only look at inorganic materials, but can look at organic material. Very useful for the gas industry. Martin Danisik's in the room, and Martin was successful in winning another Australian Research Council grant to build the West Strand Thermochronology hub, or WATCH. And that is a series of integrated tools, including a laser system, a helium mass spectrometer for uranium-helium dating, fission track stage for looking at low temperature thermochronology, So in the temperature range now, you've got between, let's say, 70 degrees Celsius and 180 or 200 degrees Celsius for understanding things like fluid flow in the crust or exhumation histories of continents. And another interesting tool that he has is he needs to measure the volume of pits that his laser drills, and it's a 3D optical profiler. So here you can see that pit volume of that laser being 1,000 cubic microns. So yeah, Martin's in the room, and certainly he'll talk to you about what he's doing. There was an announcement with funding from both the OSCOPE, that's the NCRIS, the Commonwealth Government Research Infrastructure Program, as well as the Geological Survey, to replace that 25-year-old shrimp with a new ion probe. And this tool, ECA 1300, this is what will be installed the first quarter of next year. It will allow us to be able to analyze stable isotopes as well as radiogenic isotopes. And here's a map, if you will, this is a diamond, a complex growth of a diamond. And here's the carbon isotopic map of that diamond. So it's going to allow us to bring into different samples into the center. So not only will we be able to age date materials, but we'll characterize them isotopically, provide you with information, what the mantle sources may have been like. Was there a subduction component? And another new direction is we're moving away from the 2D and moving more into the 3D. And so the idea here is we're going to get a Xray CT system, which is going to allow us to do whole core analysis and a workflow, including automated mineralogy, to characterize materials in the third dimension, in the mineralogy in the third dimension. An example of this is the tool that we're going to be building. It's on order now. It'll be built next year. It's called the Xray Scan. Here it is in the laboratory environment, and it's analyzing here part, I believe, in this instance. But here is a typical example of what a chondrite, a Murchison chondritic meteorite looks like. And you can see here it's differentiated the chondrules in terms of this isovolumetric space. And also the light yellow is iron nickel alloys and iron sulfide minerals in the. So we're looking forward to this tool coming on board. A new direction for the JDL is additive manufacturing. This is a tool that Zach Kadir is responsible for. Zach is a metallurgist who is also the director of our microscopy facility. And there's a reason for a specific reason for this is that whenever we do any sort of work with additive manufacturing, it needs to be metallurgically tested, and that's tested in the center. So it's appropriate that these sort of tools are integrated with the JDL. This is again well over $1 million. This is a very large box containing this 6-axis robot with a laser print head. Here's the complicated laser nozzle and 4,000 kilowatt laser. 4 kilowatt laser. Each of these inputs is where you can put various metal powders. So these are metal powders here that get fed through into the laser nodule and then basically sintered onto the side of a part. So we have the ability to automatically track where existing components are damaged for automatic correction and repair, but also we can surface deposit wear-resistant metals on top of existing materials. And we can actually change composition of metal through time in the component. So this is something that's quite unusual. So big deal, why? Why is this important? Well, this is important to the minerals industry who might want to have specially designed components and parts for them. Later center as well. So in Final piece of information is that I mentioned before, we're running out of room. There's been a lot of discussion, a lot of planning around a new building that will be built on campus. And the core research facilities of the Laeter Center and other research centers in the university will be placed in the building here. It's called Building 316. Probably also host the West Strand School of Mines. And we're very excited about this as our future destiny. Thank you very much for your time.